Welcome to the assignment presentation of the course Communication System 2. I am Sai Pranav. In this presentation, I will explain about silicon-based millimeter wave phased arrays for beamforming. Every wireless generation provided faster speed and more functionality. 1G bought us the very first cell phone. 2G let us text for the first time. 3G bought us online. 4G delivered the speed that we are enjoying today. But as more users coming online, 4G is reaching its limit, what they are capable of. Now it's a time where end devices need more data and speed. The one-stop solution for all this is 5G, which can handle 1,000 times more traffic than today's network and 10 times faster than 4G LTE. 5G has come up with a certain vision and will be the foundation for virtual reality, autonomous driving, Internet of Things, and the stuff that we can't even imagine of. But what exactly is 5G? To me, 5G appears the composition of five emerging technologies or five innovative technologies that they are millimeter waves, small cell, massive MIMO, beamforming, and full duplex. So the topic of today's presentation is silicon-based millimeter wave phased arrays for beamforming. Many of our engineering at undergraduate level restrict the system level analysis, and the way it is implemented on the silicon lies in the semiconductor companies itself. Today, I would like to make an attempt to discuss the silicon implementation of the communication systems. Today, for my presentation topic, I would like to discuss the two different 5G technologies. They are millimeter waves and beamforming. Our smartphone and other electronic devices use a very specific frequency on radio spectrum, typically below 64 gigahertz. But because of they are getting crowded now, the researchers are experimenting with broadcasting on shorter millimeter waves. They are anyway between 30 to 300 gigahertz. These are called millimeter waves, and the section of interest for 5G communications is 26 gigahertz to 40 gigahertz. The millimeter waves are not recent, but they date back to the Jagdish Chandra Bose's first wireless communication experiment, where he used 60 gigahertz millimeter wave. The advantage of the millimeter wave is that millimeter waves make it possible to have a lot of transmitters and receivers installed in a small size or a cell or a panel. The next technology we will going to discuss is beamforming. The current 5G signals spread over a large area. Thus, the signal tend to lose energy more quickly. To make it worse, when different users tend to interfere with each other if they stand close. Beamforming makes the transmission between the users and the base station more directional. This leads to less interference and less energy consumption. So now we have understood what millimeter wave is, what beamforming is, and now let us see what are phased arrays and how is it implemented on silicon. So before understanding some phased arrays, we need to understand some basics of radiation pattern. So in radiation pattern, there are two types of radiation pattern. One is the polar radiation pattern, and another one is the rectangular radiation pattern. In polar radiation pattern, the radiation pattern is modeled as at the center or at the origin, we will have the antenna, and in the polar coordinates, we represent the directivity of the antenna. So now we can observe for this particular radiation pattern at 0 degrees, we have a main lobe, which means our radiation from the antenna is directed to this particular direction. So when we unfold this particular polar radiation pattern, what we obtain is the rectangular radiation pattern. So on the rectangular radiation pattern, the x-axis will be the direction or the angle, and the y-axis will be the directivity of the electromagnetic spectrum. So this is the main lobe of the radiation pattern, and these are all the side lobes which will have less energy, and this particular main lobe will have the more energy, and we need to direct this to the particular user in order to achieve the communication. So we have understood that antenna is a radiating element. It has a radiation pattern around it. So now in order to make this more directional, when we take two antennas and give the same signal, then the radiation becomes more directed. If we increase from 2 to 4 antenna strips, then we get still more directional antenna, directional radiation pattern. So what we have observed is that we get more directional radiation pattern when we have an array of antennas. So this is an antenna array which will provide a very directed beam of radiation. So now we have to achieve the steering of this particular directed radiation. So what we need is this particular steering. So we should be able to steer this particular radiation in any angle we want. So for this, we need to give different signals to all the antenna array elements. So what are those different signals are? These are the phase shifted copies of the same signal when provided in a particular phase shift pattern, and when the antennas are separated at a distance of lambda by 2, we can steer the beam at any particular angle. So what we have understood that by providing the phase shifted copies of the same signal, we can achieve the beam steering. So this is how it's possible. Now let us see a MATLAB simulation of this beam steering. So I'll just execute this beam steering. I would just like to show you. So now there are two antennas separated at an angle lambda by 2. So now this is the phase difference between those two antennas. So whenever it is 45, 49, it's basically increasing. This is how the direction of the radiation, the main lobe of the radiation pattern, this is how it varies. And in this way, we can steer the radiation pattern any direction we want. So let me stop this very simulation. So now we have understood that how this simulation varies. So this is the faster version of the same. So this is how basically by changing the phase shifted copies, by providing the phase shifted copies to antenna array, we can achieve the beam steering. So what we have observed is whenever we have antenna, this is a 10 antenna arrays. When we provide the same signal to all these antenna elements, we get more directed beam. So this is the radiation pattern. This is a three-dimensional radiation pattern. When we project this onto this particular plane, what we get is the rectangular radiation pattern. So this rectangular radiation pattern is again represented here. So now, since we are not providing any phase shift, it is basically directed at 0 degrees. So now at 0 degrees, we have our main lobe. Now, when we provide phase shifted copies to the different antennas, then what we get is the direction of the main lobe is steered or rotated to particular angle. So now we can see that this is the projection of the three-dimensional radiation pattern on this particular plane. Now whatever we are seeing in the red color is basically after giving the phase shift. So for comparison, we can compare with the 0 degrees or unshifted copies are provided to the antenna array. We can compare that. Now we are having a separation, which means the direction of the main lobe is basically steered. So that's why this is a antenna array. When we provide different phase shifted copies, we get the steering capability for the particular antenna. So that's why this type of antenna, in which we have a capability to steer the antenna by changing the phase of the signal provided to each antenna, is called a phased antenna array. So now we have understood what a millimeter wave is, what a beamforming is, and now we have also understood how to achieve beamforming using millimeter waves, that is by using phased arrays. Now let us see the silicon implementation. As a case study, I have taken IBM silicon-based phased array, which is at 28 gigahertz. So this is the IC architecture. So this is basically a transceiver, which means this consists of both transmitter as well as receiver. This particular switch, when connected to this side or the left side, it acts as a receiver. When it is connected to the right side, it acts as a transmitter. So this is these two are multiplexer demultiplexers, and these are the antennas or front ends of the particular RF circuit, RF system. And this has a transmitted IF of 3 gigahertz and transmitted an RX IF of 3 gigahertz. It has an input LO of 5.2 gigahertz from a frequency synthesizer. It will be quadrupled, and it enters the quadruple frequency will enter the IC. Now let us see the transmitter or transmitter path. So in the transmitter path, we get from the baseband processor, we get the 3 gigahertz intermediate transmitting frequency, which is split into the IQ phases. Basically, here it is this is basically a dual up conversion heterodyne. So which means it has two up conversions. So one is at this particular point, it gets up converted. And after following this at near the RF front end, it again gets up converted. So basically it's a dual heterodyne up converter. The transmitter is a dual heterodyne up converted, and it reaches the RF front end, and it basically gets transmitted as electromagnetic waves. And coming to the RX path, from the signals are collected from the transmitter, I mean from the antennas, and these are multiplexed. These are this is a dual heterodyne down conversion mixers are there. So basically two-step down conversion is there here. And finally we get 3 gigahertz IF signal, which will be sent to the baseband processor. So coming to the front end, front end has a lambda by 4 lines, T lines, for implementing the phase shifted versions. So this is how each IC is having basically 16 front ends, 8 on each side. So this is the implementation of the particular chip on 130 nanometer by CMOS technology. So we can see that the antennas, or the 16 antennas, take so much space on the silicon compared to the RF circuits present in the chip, on the chip. So this is the final PCB. IBM has abutted 4 such ICs to form the final PCB. So basically 4 such elements, as we can see, this is the top and this is the bottom of the particular PCB. Now, this particular ICs will be again abutted on a base station transceiver or base station transmitter system, transmitting receiving system. For this purpose, whenever they're abutted, there can be some interferences that can cause. That's why the PCB has 36 dummy antennas placed. So whenever such PCBs are abutted together, then the interference chances will be less. So this is the design of the IBM's 28 gigahertz 5G transmitting RF chip. So let us see some other on technology 5G or 6G enabled chips. So this is a chart representing the recent or very recent improvements that have come on the RF front end of the 5G systems. Among this, the highlighted ones are suspected to be used for 5G because they fall in the frequency spectrum of the 5G. Among this, the first one, this is what we have discussed. This is 28 gigahertz transceiver receiver chip, which is consisting of 64 antennas. This is what we have discussed just now. Others are Qualcomm IMS, which was released in 2018, UCST TMTT, which was released in 2018, and the Samsung ISS-CC, which was released in 2020, and ADI's ISSC 2021, which is designed at 28 gigahertz. And these are suspected to be used for 6G. So IBM, Bell Labs, IBM's ECTC 2018 releases are supporting higher millimeter wave technologies like around 94 gigahertz. We can see the IBM's ECTC 14 and ECTC 18 support 94 gigahertz transmission, and the Bell Labs ISSCC 2018 supports 90 gigahertz transmission. One more interesting design that was developed in 2018 is Broadcom ISS-CC 2018. So this is a very peculiar design because every design we can observe the number of antennas are in the powers of 2. So, but this particular has a peculiar 48 antennas per tile, so which is very very surprising design, because it's very hard to achieve this kind of skewed number of antennas on a particular chip, because we will always get in a multiplexing demultiplexing, in order to have a proper phase shifts, or we need this powers of 2. But this particular release of Broadcom ISS-CC 2018 surprised many manufacturers of this RF chips. So this is the 5G base station. So basically the 5G base station employs such PCBs, many PCBs abutted together, and this forms the base station or cell site of the particular 5G small cell. So this is all about my presentation. In this presentation, we have discussed about how phased arrays are implemented on silicon chip. So this is all about my presentation, silicon-based millimeter wave phased arrays for beamforming. Thank you.